having just looked at an example of solving a second order differential equation using Laplace transforms when we have a step function, we're going to use that same kind of idea now to look at a mixing problem. And if you remember, the one on test 2 looked very similar to this, but on test 2 we did it manually by first solving the problem for the first 10 minutes. So you have the first 10 minutes, the flow is coming in from A at 6 liters per minute with 0.04 kilograms per liter. And then after 10 minutes, the valve switches and the B flow kicks in. And so on test 2, we solved this manually by solving the question for A and then plugging in t equals 10 to find the initial value for the second problem. So we kind of thought of it as two separate problems. Using Laplace transforms, though, we can actually handle it all at once, and the algebra does get fairly messy, so be aware of that and be ready for it. But we can do it all at once, and it ends up, since we have this kind of discontinuity, this discontinuous input, which it shifts at one moment from A to B, you can think about how that's going to be affected by unit step functions or like a pulse function. In this case, it's a well, a combination of the two. So that's the setup, is we have this valve that switches things. And as always, we start a mixing problem by looking at the rate in minus the rate out. The rate out, notice that both inputs have a flow rate of 6 liters per minute, as does the output. So the rate out is just going to be 6y over 1,000. Since the level of brine in the tank stays constant at 1,000, we just have a denominator of 1,000. And then we have our initial condition, of course, as well. So the key to this problem is that since the rate in changes, we're going to label that g of t, and I've written down what g of t is. It's this, again, discontinuous function, where for the first 10 minutes, it's 6 liters per minute times 0.04 kilograms per liter. So that's 0.24 kilograms of salt per minute. And then from starting at t equals 10 and from there on, it's half that, because the salt concentration gets cut in half, and so it drops to 0.12 from that point on. And now that we have seen the pulse functions and the unit step functions, we can rewrite g of t using those. So the initial value from 0 to 10 of 0.24 would be using the pulse function from 0 to 10. And then from then on, it would be 0.12 using the unit step function shifted by 10. So that's the another way to write down g of t. And again, the reason for doing so is that we can use what we know about the Laplace transform of the pulse and unit step functions. Before we talked about those, we could also have found the Laplace transform of this the hard way, doing the integral manually. But this, of course, is easier because we can jump straight to the answer. So our differential equation ultimately looks like dx dt equals the rate in we're calling g. So that would be, well, I'll do it this way, g of t minus the rate out, which is 6y over 1,000, or 6x. What am I using here? I'm using x. Sorry, that should be x. 6x over 1,000. So then, just rearranging, we'd have dx dt plus 6 over 1,000 is 0.006 x equals this g of t. Okay, and with that, we're ready to take the Laplace transform in order to solve. So we take the Laplace transform of dx dt, the derivative. That would be s times capital X minus x of 0. Then plus 006, capital X. And then on the right-hand side, the Laplace transform of the pulse function would be 0.24 times e to the 0t, so that would just be 1, minus e to the negative 10t, or negative 10s rather, all over s. And then plus 0.12, then the unit step function, that would be e to the negative 10s over s as well. Now notice we can combine some pieces over here. So this would be 0.24 times 1 over s, and then plus 0.12 minus 0.24 times the rest. All right, so that equals the left-hand side. We can factor out an x, capital X, and then x of 0 was 30. So then, as always, we're going to solve for capital X, and then we're going to have to do a partial fraction problem and then work backwards. So solving for x is relatively straightforward. Notice that the right-hand side is all divided by s, so we're going to do the same thing when we move the 30 over. We'll also divide it by x, or by s rather. So I'm going to have 0.24 minus 0.12 e to the negative 10s. And then when I add the 30 over here, I'm going to multiply by s and divide by s so that I can get one common denominator and one fraction on the right side. So that then x is going to be all of that divided by s times s plus 0.006. All right, and then to break this down, we're going to do the partial fraction problem on this. So doing the partial fraction decomposition, we're going to have all of this is going to equal a over s plus b over s plus 0.006. So again, multiplying everything out, we would have 0.24 minus 0.12 e to the negative 10s plus 30s equals a times s plus 0.006 plus bs. So again, you could do it by plugging in s equals 0 and s equals negative 0.006, but especially with that exponential term, that's just going to be messy with the coefficients. So it might be easier to do it the other way, to add things, or to expand things out and then equate coefficients. So the a plus b have to add up to 30, and then 0.006 a will equal the remainder, the 0.24 minus all of this. So then if you divide both sides by 0.006, you have a equals 0.24 divided by 0.006, which is 40, minus 0.12 divided by 0.006, which would be 20 e to the negative 10s. And then if a plus b equals 30, b equals 30 minus a. So 30 minus 40 would be negative 10, and then plus 20 e to the negative 10s. So putting that all together, x is going to equal, it was a over s, so 40 minus 20 e to the negative 10s over s, plus b, which is negative 10 plus 20 e to the negative 10s over s plus 0.006. So again, to do the inverse Laplace transform, I'm going to split this up and kind of make one, take one piece at a time to make it easier to look at. So I'm going to write this as 40 over s minus 20 times e to the negative 10s over s, and then minus 10 over s plus 0.006. Plus 20 times e to the negative 10s over s plus 0.006. Then we can take each piece one at a time. So again, I'm going to label these just for the sake of keeping track of everything. So number one, the 40 over s, that's just the very first Laplace transform we saw for a constant. So that would be the inverse Laplace transform, that would be just 40. The next one, the 20 times e to the negative 10 of s over s, this right here, if you look at your Laplace transform sheet, that looks just like the unit step function with a equal to 10. So it's shifted over by 10. So that would be 20 times the unit t minus 10. Then the next one, the 10 over s plus 0.006, that looks just like the simple e to the at. So that would be s minus a in the denominator. So a would be negative 0.006. So that's the exponential. So the 10 gets carried along, and you have e to the negative 0.006 t. Then for the last one, number 4, this one will take a little bit more work, but you've got the, let's see how to say this, you've got the basic form of the exponential one, except that you have the addition of this e to the negative 10s. So if you look at that, we have to compare this back to, where was it? Here we go. So we've got e to the negative 10s over s plus 0.006. So if you're comparing these, we're looking at one of these right here. And since the we have e to the negative 10s, the a is going to be 10, and it looks like we can use this first one here, maybe. Let's find out. So there's a reminder. Let's write that down and see if it works. You kind of have to take this slow sometimes. You can't jump straight to the answer. So just as a reminder, we have this one is e to the negative as times f of s. And this one here is e to the negative as times the Laplace transform of f of t plus a. So let's see if we can make this work with the first one. So if we can, then a would be 10, and then the remaining f of s so if here we have e to the negative 10s times 1 over s plus 0.006. A would be 10. Capital F of s is this here. So that means f of t would be e to the negative 0.006t. So it looks like it'll work. And if we work backwards then, that means that e to the negative 10s times s plus 0.006, the inverse Laplace transform would be this piece here. So that would be f of t minus a, e to the negative 0.006 times t minus 10. And times the unit step function, t minus 10. Right, so again, it's a little tricky to follow all this through, but looking back, we found this form here and then split it up and said the remainder must be capital F of s, which means f of t is this one, and then we can work back to this form here using 10 for a. So we've got that last piece, and that's probably the trickiest piece of all of it. All right, so putting it all together, I guess there's a 20 on that last one, isn't there? So I should put the 20 on here just to be consistent. But then putting it all together, we have x of t equals the first term, which was 40. Then we had minus 20 times the unit t minus 10. And then minus 10 e to the negative 0.006 t. And then plus that last term is the 20, and then the exponential times the unit step function. So I get a little more room here. It's a long answer. But finally we've got it. Okay. So what this means is that part of these answers only apply before t equals 10, and then after t equals 10, some more of them could kick in. So if you wanted to write this in piecewise form, before 10, the only pieces that would be in the answer would be the 40 minus the 10 e to the negative 0.006t. And then at 10, you would have those plus all the others. You get the idea. All that. So the first part would just be for t less than 10, and then for t after 10, you would have the full combination. And of course, you could combine these first two terms and so on. But basically, the switching the valve over means that you have everything you had up to that point plus some new stuff. So it's a long problem. It's a complicated problem. Lots of details to the algebra. Lots of things that can trip you up. But it's just another way to take on a hard problem like this using Laplace transforms. Whether it's easier than the first version or not, I'll leave up to you to decide. I have a feeling that you, at this point, would prefer the first version just because it's more familiar. It's something you've done more. This version is a little bit less familiar, a little bit shakier, but it gives you another tool in your toolbox to be able to tackle hard problems like that.